Okay, so great. So now we're going to have the final talk of the morning session of the second day. And we have Nan-Kuo who will speak. Thank you.
Thank you. Okay, so first of all, I would like to thank the organizer for giving me the opportunity to talk here. Yes, yeah. So since this is a workshop on toric topology, I will try to show you some convex polytope. So it does appear in the story as we go on. And in fact, that was actually the starting point of this loan project with Martin Guest. Okay, so the plan is as follows. So I will give you some kind of motivation, and then I will explain what Toda equation is. And it corresponds to certain meromorphic connections. And then so we will look at the monodromy data corresponding to those meromorphic connections. And then lastly, we will look at the geometry that we found, which is related to symplectic groupoid. So this is joint work with Martin Guest. So it's a loan project. Okay, so first, so the TT star stands for topological and anti-topological fusion. So in 91, Chakotay-Vafa, they introduced this concept. The point is to study the deformation of supersymmetric quantum field theory. And so in that paper, they made a lot of physical prediction about what property the solution should have. In particular, they studied this special type, which is the Toda type. So this is a mathematical formulation. So it has to do with Dubrovin as well. So this is called the TT star Toda equation. So it's a Toda type. We will look at this equation later on as well. So I'm not going to talk very much about this equation. So the point is that you would have families of this equation. So I is in the integer, so W0, W1, and so on all the way. So it's periodic. So W0 will be the same as Wn plus 1. This radial and its anti-symmetry. So Wi plus Wn minus I is 0. So this equations, its PDE is quite difficult to solve, but in 2015 and 2023, so the lower rank and the higher rank, it's done by Martin Guest, Alexandra Itz, and C.S. Lin. So they solved this PDE, and then also they studied the asymptotic behavior of the solutions. So in particular, they solved these equations, which means that, because this is defined on C star, so it means that the solution is defined on the C star. So they solve it, and they show that it has this particular asymptotic behavior. So Wi is having this kind of asymptotic behavior. So it's half of gamma I log t. So t is the variable on C star. So it is a one-to-one relation with this convex set. So on the left-hand side, you have the set of all global solutions. So remember that we have this anti-symmetry. So W0 is minus of Wn. On the right-hand side, you would have this convex polytope. So this is gamma 0 to gamma n. This is corresponding to the solution. So this is in Rn plus 1. It has this inequality and equality over here. They give you a convex polytope. So we can look at some lower rank picture. So for instance, the lowest rank is n equals to 1. So that represents SL2C actually. So you have global solutions. So in principle, you have W0 and W1 because of anti-symmetry. So W0 is minus W1. So it's bijective to this set. So over here with the relations, then what you have is this closed interval. So that's the first set it corresponds to. And if you look at n equals to 2, then you have W0, W1, and W2. So the anti-symmetry tells you that the middle part has to be 0. So W1 is 0. And then W0 and W2 has this minus sign difference. So the right-hand side still gives you this closed interval. Now, if you look at n equals to 3, which is SL4C, then you start to see this polytope appearing. So W0 is minus W3, W1 is minus W2, and on the right-hand side, with all this inequality, now you have this closed triangle. So this including the boundary. So this is a convex set appearing. So what happened is that because this is a bijection, so that represents that the solutions is in one-to-one corresponding with this convex set. So any point inside of this convex set, it gives you back as solutions. And this representing by this asymptotic behavior as your T approaches to the pole. Okay, so in this long project with Martin, so we gave a least theoretic reason why this convex set show up. So we will also show that in the later slides. But so the other question is that because this is one-to-one corresponding with the solution, so if we want to look at geometry, then there's not much else we can say about this space. So what we would like to do is to see some kind of a geometry. So that means that instead of only consider global solutions, we would like to consider more solutions. So for instance, we want to consider the so-called local solutions. So as long as there are some part in C star which satisfy this equation, that's called the local solutions. So as you can see this picture, even in the lowest case, so this is n equals to 1. So this is the lowest rank case. You already have very interesting geometry. So in that case, SL2C, so it's a result in Guest and Hertling in 2017. So they show that if you look at the space of all local solutions, then it corresponds to, so it's also one-one correspondence, corresponds to this full whole sphere. So this is full whole sphere. And it's not complete, it goes to infinity. So it goes to infinity. And you can parameterize this. So there is a precise way of writing it, and they will parameterize your Stokes data and connection matrices as well. In particular, they show that this full whole sphere can be decomposed into 14 different strata. So for each strata, it represents different type of solutions. So for instance, the interval that we saw earlier is over here. So this represents the global solutions. So over here, it will represent other type solutions. So that in particular, that's the solution which are smooth near zero, and we don't know what the behavior is when it goes far away. So this is the lowest rank. And then so for us, what we would like to do is we would like to know what happens in general. So for the higher rank, what exactly is the geometry if you consider the space of all solutions? And then so today's goal is to sort of tell you what kind of geometry we find so far. Okay, so recall the first slides about this TD star equation. So the Wi is functions defining on C star, so they are real valued and satisfy this equation. So this is basically Toda. Okay, so this is PDE, and it has this 3 conditions that has to satisfy. So this is what we saw earlier. So this is periodicity. So Wi equals to Wi plus n plus 1. And
I'm sorry, where does n come in? What is n?
okay, so n in the next slides you will see. So that represents when you corresponding to the meromorphic connections, that corresponding to the structure group. So this n representing, so from 0 to n, you have n plus 1. So that representing the group, which will be SL n plus 1. Or you can think of it as the bundle. So that's the rank of the bundle. Okay, so that's that. And so the important condition is that it's radial. So even though this is on C star, but actually only depends on the distance from 0 to that point, not the angle, and it satisfies this anti-symmetry condition. So for the lowest rank, That's the Sy-Gorton equation, which this equation was discussed in detail in the Chakravarti's original paper. So they discussed this in detail. So that's the Sy-Gorton equation. Because over here, you can see the right-hand side. This part is the hyperbolic sine. So this equation was discussed and it was presented in a mathematical way by Dubrovin. So in 93, we showed that those equations corresponds to a family of meromorphic connections on CP1 with structure group SLN+1C, which has the isomonodromic property. So what it says is the following. So you have this base, which is the CP1, and then you consider the principal bundle, which is SLN+1C. And then on that, you consider meromorphic connections. So which means that you have pole, but the pole singularity is controlled. So its order pole is not like general singular ones. So it has pole of order certain things. And it corresponds to a family of them. So that's the T is the variable that we saw earlier. So the C, so this is a real number. So it's a family of them and has this isomonodromic property. So we know that in general, for a connection, you have holonomy corresponding to it. This is the smooth case. Now, if you consider meromorphic connections, which means you have pole, then at poles, you will have extra condition, which is the Stokes data. So isomonodromic means that within the family, as you're moving, the monodromy data remains the same as you're moving inside of the family. So that's called isomonodromic. And so those connections can be written precisely in terms of local coordinate. So let zeta be a local coordinate, then the meromorphic connections can be written as such. So over here, you can see this is pole of order 2. So the coefficient over here is minus capital W transpose. So W, capital W is this matrix. So on the diagonal part is 0. And here you have this exponential, and the rest of them are also 0. Okay, so this is that. And this X is the parameter of this family. So it shows up here. So X and X squared. So this is the expression of these families of meromorphic connections. So we know that for meromorphic connections, usually we say that D plus the meromorphic connections corresponds to the meromorphic ODE, but because we would like it to be in a better form, so we consider instead the D minus the transpose of the connection, then that also corresponds to the meromorphic ODE. So this is a flat one, so D minus alpha hat transpose. So you see that the coefficient here is transpose, so that's just the W. So from this meromorphic ODE, you see that you have pole here at 0, and this corresponds to the pole at infinity. So they are both order 2 pole. So this is the meromorphic ODE. So this is the general idea. So if it's just smooth, then you just consider the holonomy, which is like you're going around the generator of the fundamental group of the underlying surface. Now, if you have pole, then suppose you number them as such. So let's say you have n different pole, then you number the first new one as the degree 1 pole. So if it's degree 1, then you only have monodromy, formal monodromy exponent. And if you number the rest of them, which have pole of order higher than 1, then they will have this Stokes data. So we'll give a short explanation of what Stokes data means. And connection matrices representing that basically is like a parallel going from some smooth point to the pole itself. So you would have as many to the pole. So that's the essential data.
So this data is going to describe the geometric structure you're talking about, is that?
So yeah,
Is it-
so
did-
this is the so-called Riemann-Hilbert correspondence. So on one side, you have these equations. On the other side, you would have this algebraic data, which are these matrices. So those are matrix. So like SE, those are matrix in the structure group. Lambda here is in the Lie algebra of it. So that will describe what the connection is. Yes. Okay, so now let's try to have a sense what the Stokes matrices are. So starting with a meromorphic ODE, so you have a pole, let's say it's at 0, then the standard theory tells you that there is a unique normalized formal solution. So the trick is that the formal solution does not converge. So it doesn't converge on the whole C star. But it will converge on a smaller region. So those are the sectors we will see next. So what you do is you're looking at the leading coefficient of your meromorphic ODE. Using that, it will give you the so-called singular direction or Stokes directions. So those are the theta k. And pi over 2 is because now you are considering poles of order 2. So there is this sector. So this is one example of this Stokes sectors with singular, with singular directions. So in general, singular direction doesn't have to be evenly distributed, but for this TD star Toda system, in fact, it is evenly distributed. It's very nice. So as you can see here, so with the leading coefficient, that only tells you what the singular directions are, but the numbering is your choice. So let's say you decide to code this one as 1, and then you decide the orientation is counterclockwise, the numbering. So this is theta 1, this is theta 1 plus 1 over 4, because we are in SL4C here, all the way like this. So the numbering just can go around and round. And so as you can see, the omega 1 is using the theta 1 minus pi over 2. So this is theta 1 going back pi over 2. And the other side is the previous single direction, so which is this one, going forward pi over 2. So this is the red part. So this is the omega 1. And for omega 1 plus 1 over 4 is using this line. So this is the single direction that you are using, and then minus pi over 2, and then the previous single direction, and then going over in that direction. So the theory is that in each sector, in fact, there is a holomorphic solution. So we were saying that the formal solution doesn't exist. It doesn't converge. So it's just a formal one. But in the right size, you actually have a holomorphic solution. So the trick is that this sector, if the size is smaller, then you will have more than one solutions. But if too big, so if it's bigger, then you don't have solutions. So at the right size, you will have a unique solution, which is holomorphic. And corresponding to the formal solution, the relation is that as you approach the asymptotic, so the asymptotic of this holomorphic solutions is the formal solution. So as you approach this to 0. Now, from this graph, you already see that the red one and the green one has overlapping, which means that on the overlapping part, they has to be differ by only constant because it's unique. So that's the Stoke. Okay, so that's the Stoke. So the Stoke is the difference between this consecutive solutions over here. Consecutive solutions over here. So usually it's the Stoke matrices, but we try to, so this is Stokes factors that you just look at the singular directions for each one. So those are QK, which means that SK is the product of those QK in between. So that's the Stokes data at the pole 0. So similarly, at infinity, you can do the same thing. So you will have singular direction, you have the Stokes data. So you have all this Stokes sectors, and this is holomorphic solutions, Stokes vector, and Stokes matrices. So what happened between this two pole? So in the current situation, we only have on CP1, we have two poles at 0 and infinity. So the relations between these two poles is characterized by this connection matrices. So basically, you just go analytic continuation from one pole to the other. So that's the EK. So this is the EK. So now you have this set of data. So that's the general situation that you will have if you have a meromorphic ODE, then you will have all those data. You have the connection matrices, you have the Stokes matrices. So to get the corresponding monodromy data for our particular system, the TD star Toda equation, we have to use those symmetries that we saw earlier. So those symmetries on the equations can be translated into symmetry on the connection form. Okay, so these are the symmetry on the connection form. So the first one, this is the cyclic symmetry. So as you can see, what it does is it's rotating. Okay, so zeta is the variable, right? So omega is the roots of n+1. Oh, sorry, the n+1 roots of 1. And so you are rotating with this angle. So that's the Toda condition. And you have the anti-symmetry now is becoming expressed like this, theta and C reality. So those tau, sigma, theta, C, they are the algebra automorphisms. They have very concrete expression and they are quite simple. They are conjugated by some constant matrix, and then the coefficient themselves, sometimes they have to do a transpose, sometimes you have to do a bar, but in general, the formulation is not very difficult. So it's very clear and very concrete. So those symmetries will have some effect on the Stokes data and connection matrices, right? So the cyclic symmetry on the Stokes vector implies that those Stokes vector can actually be attained from two consecutive Stokes vectors. So in general, you have Q1 plus 1 over n+1 and so on. So you have everything. But in fact, you can obtain all of them from two consecutive ones. So this is due to cyclic symmetry. So in Jael's paper, they get it from doing computation precisely using those symmetries. And also the formal monodromy, is also trivial in this system. So it's also by calculation. So then the holonomy around the pole is as follows. So what does holonomy mean? It means that you go around the pole, right? And then that's the holonomy. So that's say psi 1 is your holomorphic solutions. So you go around once, then the difference, this part is your holonomy. So that's S1, first Stokes, second Stokes, and then your formal monodromy. But now because it's trivial, so that's just identity. So the holonomy is the product of S1 and S2. And because of the cyclic symmetry, so actually it's basically just QQ pi. So the plus minus representing that depending on n+1 is even or odd, you will have a minus sign. So that's the QQ pi that you will see. And the seriality relates the Stokes data at infinity to 0. Because as you can see, the seriality here, this is zeta, this is 1 over zeta bar. So it gives you this hint that it should have some kind of a relation between 0 and infinity, okay? And indeed, it does tells you all those things. And the definition for the connection matrices and the seriality conditions implies that all the EK also are determined by E1 and QK. So from the monodromy data's point of view, the building block for our monodromy data is just Q1 plus 1 over n+1 and E1. So that should tells us all the things that we want to know, plus symmetries, right? So there are still other symmetry we haven't mentioned. So the space that we want to study, this S local, the space of all local solutions. So it starts from S1, S2 at 0, S1, S2 at infinity, connection matrices, and their monodromy, formal monodromy exponent together with symmetries now becomes just S1, S2 because C symmetry, and then E1 together with symmetries. And now it's Q1, Q1 plus 1 over n plus 1 E1 symmetry. So now it's this set that we want to consider, and we will see how the symmetry act on this space. But in order to know how this Q1 plus 1 over n plus 1 act, we have to recall some of the results. Oh, sorry.
This information here,
Mhm.
does it characterize all of the solutions of the equations that you're solving?
All the local solutions,
I
yes.
see. Thank you very much.
So they're like parameters for that space that you threw in the first picture.
Yes.
Yeah.
Thank you. Right, so we would like to know what they are. So let's recall some of those results. First, so this is because I was saying this is a long project with Martin Guest. So we generalized the TD star Toda equations to any complex simple Lie algebra. And in fact, the vanishing of the formal monodromy is a general truth for all. So this is because in order to get that formal monodromy, what you do is you are projecting the leading coefficient into the catan of the second coefficient. And the system appears in this TD star Toda system is that they lies in two different catan, and they are the so-called catan in opposition in the language of custom, which means that when you do the projections, it vanishes. So that's what happened. So this is true in general. So that also explains a calculation result. And then moreover, the singular directions has very nicely geometric description. So for each G, so of course we know that there is this Coxeter number S corresponding to different Lie algebra. And then this precisely is 2S singular directions, and they are evenly distributed. So the singular directions are evenly distributed for all cases, and the number is 2 times the Coxeter number. So for our AN type, that's n plus 1. So that's why you have 2 times n plus 1 singular directions in the AN case. Okay, and in fact, they can be identified with the rays in the Coxeter plane. So like if you Google Coxeter plane or Coxeter element, then the Wikipedia will show you this picture, this colored thing, and has many, many dots. They representing the roots, right? And then so if you draw the rays from the center to those dots, then that's the singular directions, which actually matches. And what's even nice is that this tells us the shape of our Stokes vector. So remember that we were saying that the Stokes vector are something in the Lie group. So that's in fact corresponding to the roots on each singular direction. So on each singular directions, because you know that you can identify it with the rays in the Coxeter plane. So there are certain roots on that ray. And then that roots actually tells you what the shape is. So we will see on the next slide what precisely the shape look like. Sorry, the next slide. So it also has this property, which is that the Coxeter element gamma, this is determined by the systems as well. So once you know the coefficients and the system that you are choosing, then you have this corresponding Coxeter element. And the way that it acts is by rotating, it will jump one direction to the other. So like theta I will goes to 1 plus 2 over S. Theta I plus 1 over S will jump to theta I plus 3 over S. So that gives you the reason behind the computation reason that why you only need 2 consecutive ones, because that generate everything by Coxeter element. So from 3 and 4, we are inspired to define the space of all possible Stokes. So here you see that the thing, why we were saying that it determined the shape of the Stokes factor is because, so given any roots, so if alpha is a root on the singular direction theta 1, then you can consider the root space, you consider the exponential of that root space, and you do the product. So that's the first part. And then the second part is the roots on the single direction 1 plus 1 over s. So that's the second part. And then the pi is a group representation of the Coxeter element that you pick. So for different system, you will have different ones. So that's the space of all possible Stokes. The reason is because we haven't used any symmetry yet. So far, if you just pick anything in this curly n thing, then that does not necessarily coming from a solution. So you have to impose symmetry in order to know which part actually would correspond to solutions. So for instance, this QQ pi that we saw earlier lies inside of this space. So one of the results is that we identified this space with the Steinberg cross-section of conjugacy classes of regular elements of G. So S1, S2, those Stokes data are not necessarily regular. They may not be regular, but M will be. So QQ pi will be regular, which is very useful for us later on, as you will see. And this is not relevant to the later part, but it's just tied back to the convex hull that we saw in the earlier slides. So the result says that there is a one-to-one correspondence between this W. So this is the local solutions near 0. So they're QQ pi. And this fixed point set on the fundamental well alcove. So this sigma map is group Lie algebra homomorphism. This is a Lie algebra homomorphism. So this is the same as the one which Hitchin defined it in his Lie group and Teschmiller space paper. So that's the same sigma. And so it has this effect on the fundamental well chamber, well alcove. And then so that gives you the convex set. So in the n plus 1 case, so in AN case, that gives you back the shape that we saw earlier. So that's the Lie theoretic reason why this is the convex set. So now what we have are the following. So we have some information about how you analyze those Stokes data, which is the QQ pi thing. And instead of looking at them as two different matrices, you look at the product with pi. So instead of looking at Q1 plus 1 over n plus 1 and then E, we look at the M. So it is the product of QQ and pi. So you look at these two elements, and again, you have symmetry. So if you look at M and E1, so the natural one, it's not very nicely, their relation are not very nice. So we modify the E1 a little bit. So we modify the E1 a little bit to E. Then we actually have this commuting relation. So this M and E becomes commuting. So the space that we want to consider now translated into this very nice description. So that's E, this is M. So E is this matrix which will commute with M. And then M, because it's QQ pi, so it lies in this curly n plus 1. So this commuting. And the symmetry are theta and sigma, which are induced by the theta and sigma earlier. So remember that we wrote the theta and sigma on the connection form, which are on the Lie algebra, it's just like conjugating with some constant matrices. But once you translate it into this monodromy data space, the theta and sigma becomes quite complicated. It's no longer constant. Oh yeah, so this set is without the symmetry, that's the universal centralizer. So in BFM's paper, they mentioned this. So this is at the group level. So there are two different kinds of universal centralizer. There is one corresponding to the Steinberg cross-section. There is one corresponding to the Coston slice. So you have these two different ones. So how difficult is to describe this symmetry? So this theta and sigma, once you translate it several times, right? So you started with the symmetries on the connection, then you have to translate it into the Stokes data and the connection matrices, and then you have to further translate it into the modification. And so now the theta and sigma has this more complicated form. So the E and M has to do something themselves, but then they have to conjugate it by a function. So this thing would depend on M. So depending on where you apply this AM will change, as well as the BM. Okay, so it is not clear from this equation that this actually preserves the set, right? Because remember, our M is one Steinberg cross-section. And now you apply this map, sigma or theta, then it might move out of that Steinberg cross-section to a different one. So you have to actually check this. So this is just have some sense what they look like. So when n equals to even, then AN is the S1 transpose. So S1 is the first Stoke. Bn is the bar of C star Q n over n plus 1. So that's part of the Stokes data information. So it's really complicated. But indeed, they preserve the space, and turns out to be involutions. So you have to use something to show this. And turns out that groupoid is the right framework to study the space. So to us, it's quite surprising because from the beginning, there's no groupoid appear anywhere. So the result is as follows. So we show that if you consider the space of all local solutions, so this is S local, so it's described as such with this restriction over the set of all the Stokes information, so M is all the Stokes, QQ pi, then this in fact is a symplectic groupoid. It's real. We will see why it is real, but it's a real symplectic groupoid, which means that this space has a symplectic structure. And consequently, because it's a symplectic groupoid, so the base, so the unit is Poisson, and the dimension is just half. So you have this nice relations and the geometry that you can see. What time do I have?
You still have like about 7 minutes or so.
Okay.
A little bit more.
Okay, thank you. So yeah, so you will have this. So which means that there is a symplectic form, and the symplectic form is multiplicative, and so on. Okay, so from here you will see why we are using the groupoid language, because if you are only interested in having some kind of a symplectic structure on the space, you might think that why can't we just build some kind of a symplectic form on the total space, and then we apply the sigma and theta. The problem is that because theta and sigma, they depend on the point that you apply. So the tangent space decomposition at any regular point is very complicated to describe, especially once you apply the map, it becomes hard to control. So using groupoid, what you can do is the following. So we start from the AMM groupoid, which is the double. So the source and target map is as such. So it's quasi-symplectic groupoid with this 2 form and this 3 form. And the universal centralizer space, which we denoted by Z. So this lies inside of G cross G, right? And then, so you can check that this Z over this curly n plus 1, this in fact is a Lie groupoid. And moreover, on the inclusion map, this is Lie groupoid morphism, and the symplectic property and multiplicative can be checked by pulling back this two phone. So this two phone on this G cross G, this is not symplectic. So it has degeneracy. So there are some kernels. But once you pull it back over here, so over this whole Z, then it becomes symplectic. And so you cannot directly check over Z, but you can check over the unit. So on the unit, the nice thing about groupoid is that on the unit, you have a very nice decomposition of the tangent space. So that's where you can check non-degeneracy. And then the general theory is telling you that you can, if you have this multiplicative two phones, and if it's non-degenerate on the base, then it's non-degenerate on the whole space as well. So that's the first step. So onto the universal centralizer groupoid, then it is symplectic. Oh yeah, so Balivama showed also that the universal centralizer is symplectic with a different approach. So I think she was interested in different things, but in the middle, she has to show that the universal centralizer space, which is the not the M, but the Steinberg cross-section, that one is symplectic. So yeah, so using some of Steinberg result, we can show that the sigma and theta indeed preserve the space and their involutions. And one important thing is that this two thing actually commute. So because as you can see here, this is theta composed theta, sigma composed theta, this is theta composed sigma. So once you change the order, then the thing which you use to conjugate becomes different. So there is no reason why it commute. So it actually has to use some property in order to show that they commute. So now you have this two symmetry or two involution that you want to consider on the groupoid. So the first one is sigma. So you show that sigma is symplectic. So the pullback of omega c is omega. So now this, we just said that this pullback form on the universal centralizer is symplectic, right? But because it's SLN plus 1C, so in fact, this is a holomorphic symplectic form. So when you pull it back, it's the same. And you can show that this fixed point set is a Lie groupoid. So then using the natural inclusion, the pullback of this two form, the symplectic form is again symplectic, and you can show this multiplicative as well. So that gives you a first symplectic groupoid. Then you want to apply the other symmetry, right? So you apply the other symmetry. So this is applying the other symmetry, but for the other symmetry, it's not symplectomorphism. In fact, when you pull it back by theta, it's minus of the bar. So for a holomorphic symplectic form, you know, you can write it as omega 1 plus I omega 2, where omega 1 and omega 2 are both symplectic. They are real values symplectic. So because the property is minus of the bar, so the one that survived is omega 2, which is this real symplectic form. So on the space that you end up with, so once you apply this, both of them, then what you have is the pullback of omega 2. So that's a symplectic form, and it's satisfying all those multiplicative properties as well. So again, the reason that you can show that this map is symplectomorphism and this map is minus of the bar also rely on using the groupoid structure. It's like, it's possible to check it on the unit, and then you apply certain things, then you can get it on the whole space. Yeah, so it is, we would say that the groupoid comes to the rescue because it really helps us a lot. Yeah, so we are investigating some other related symplectic groupoid. So these are the reference. Thank you.